The last two videos have presented the theoretical idea of the Fourier series and the Fourier cosine and the Fourier sine series. I think it's worthwhile to at least do one example in a lecture, and then you can have other examples to do for practice. So this is called a triangle wave because the function looks like a bunch of triangles that repeat themselves. If you look at the origin here, and then the origin on the y-axis, you'll see that this function is an even function about the origin. So then it's representable by a Fourier cosine series. We can try then to derive what that series is. So let's start. This is our f of x. So we know that f is even, and the period is it goes from minus pi to pi, so the period is 2 pi. Remember, the period is supposed to be 2L, so L is equal to pi. And then we write down the Fourier series. So here it's a cosine series. So f of x equals a naught over 2 plus the sum from n equals 1 to infinity of a sub n times cosine. This should be n pi x over L, but L is pi. So then we get the pi's cancel, and we get nx. Okay? And that's our Fourier series. And then what are the a's? The a sub n's supposed to be 2 over L. So here it's 2 over pi. The integral from 0 to pi of f of x times cosine nx, n pi x over L, nx dx. Okay. So we need to represent what f of x is, this function between 0 and pi. It's just this line that starts at 1 and goes down to minus 1. So f of x is equal to 1. And then we have minus, at pi, it's minus 1, so minus 2x over pi. Okay? And that will be valid for x between 0 and pi. Okay, so that's the Fourier cosine series for this function. We have it written as a naught over 2 plus the summation over cosine waves. We've written down what a sub n is and what f is. So what remains to be done then is to compute this integral. Okay. We can start with a0. If we compute a0, what we'll find is that we get 0. So a0 is in fact equal to 0. And then if we compute an, we have to compute 2 over pi times this integral from 0 to pi of this function, 1 minus 2x over pi times cosine nx dx. How do you do this integral? You can integrate the one term first, which is the integral of cosine nx. That becomes a sine nx divided by n. But sine nx would be sine n pi and sine 0. Those are both of those terms are 0. So this one term actually integrates to 0. What about the 2x over pi term? Then we have to integrate x times cosine nx. You might remember how to do that from calculus, or at least I hope you remember. You do that by an integration by parts. It will take too much of my light board to demonstrate that for you, but you can go ahead and take a separate piece of paper and try to remember your calculus and how to do this type of integral. If you do this integral, I can look at the answer. The answer would be 4 over n squared pi squared times 1 minus cosine n pi. And the value of 1 minus cosine n pi depends on n. If n is 1, say, we would have 1 minus cosine pi. Cosine pi is minus 1, so we would get 2. So if n is equal to 1, 3, 5, we would get 2. So that would be 8 over n squared pi squared when n is equal to 1, 3, 5, odd numbers. If n was even, so cosine 2 pi is equal to 1, and we would get 1 minus 1, we would get 0. So similarly, cosine 4 pi is 1 and cosine 6 pi, so we would get 0 if n is equal to 2, 4, 6, etc. Okay, and a naught is equal to 0. So we can put that together. Then what is our f of x? So our f of x then becomes the sum from n equals 1 to infinity. Well, why don't I just take the terms separately? So the first term will be n equals 1. So we'll have all the terms will have an 8 over pi squared. And then the first term will correspond to n equals 1. So we'll have a cosine x. The second term will correspond to n equals 3 here. So we'll have a cosine 3x times a3. I already factored out the 8 over pi squared, so we just have a 1 over 3 squared. So we have a cosine 3x over 3 squared. And then the next term would be cosine 5x over 5 squared, etc. Okay, so that's our representation of the triangle function in terms of a summation over these cosines. You would never be able to guess that from looking at the picture, but that is true. There's another interesting mathematical formula you get from this expression that was quite remarkable when it was first derived. If you look at x equals 0, you see that f is 1 at x equals 0. So if we substitute x equals 0 into this expression, we get 1 on the left-hand side. So we can multiply both sides by pi squared over 8. So we get pi squared over 8. And what is that equal to when x is equal to 0? Cosine 0 is 1. Cosine 0 again, so 1 over 3 squared plus 1 over 5 squared, etc. So we get an expression for pi squared over 8 in terms of the sum of the inverses of the odd numbers squared. Quite a remarkable mathematical expression if you like this type of thing. Okay, so let me review. I wanted to give you an example in this lecture of how to compute a Fourier series. Here we look at the triangle function. We set it up so that it is an even function with period 2 pi. Then we can use the Fourier cosine series for an even function. In order to find the coefficients, we do need to do this integral, which requires integration by parts. After we do that integral, then we get the Fourier cosine series. As an added bonus, we get this famous series for pi squared. I'm Jeff Chasnov. Thanks for watching, and I'll see you in the next video.